And I want to invite our next speaker, Marc Niklas Müller, to talk about abstract interpretation of fixed-point iterators with applications to neural networks. Good job.
Hello everyone, I'm Marc Müller from ETH Zurich, and today it is my great pleasure to present you our work, Abstract Interpretation of Fixpoint Iterators with Applications to Neural Networks. Let me start with a short motivation of why we even would want to apply abstract interpretation to neural networks. Over the recent years, deep learning-based methods have achieved exceptional performance on many hard tasks. However, they exhibit a concerning lack of trustworthiness. More concretely here, for a street sign recognition task, the neural network performs well on the original image, but if we slightly rotate the image or partially occlude it using tape or graffiti, suddenly we can cause almost arbitrary misclassification. This is known as adversarial examples. While this is academically a curiosity, it can have fatal consequences if we apply such or deploy such systems for real-world safety-critical tasks. Thus, we conclude that standard accuracy is not enough for real-world AI. Instead, we require certifiably trustworthy AI. To formalize this a little bit, we want neural networks with provable guarantees. More specifically, we want, for preconditions, defining a set of inputs and some trained neural networks to know whether or not the outputs satisfy some post-condition. Or similarly, we want to say, do these preconditions imply the post-condition for a given neural network? Neural network verification is a popular tool to determine this, and a popular neural network verification approach is based on abstract interpretation. Here we encode the precondition, or really the inputs that satisfy the preconditions, using a convex abstraction, and then propagate this abstraction through the neural network, thus effectively computing an over-approximation of its reachable set. We can then compare this reachable set against the post-condition to determine whether or not it is satisfied. However, we observe the following trends. If we train neural networks without the certifiability in mind, or without robustness in mind in general, then we obtain networks with very high accuracy but very poor robustness. In contrast, if we use certified training methods to increase the robustness, we observe a severe drop in standard accuracy. Recently, a novel neural architecture called MONDEC, that is fixed-point iterator based, has been identified to exhibit empirical robustness properties without any specific training, thus raising a great interest in formally analyzing their safety and robustness. And this is exactly what we'll do. I'll first provide a short background on MONDECs before discussing abstract interpretation of fixed-point iterators, and then a novel abstract domain, the CH-Zonotope, before showing some empirical results. Here on the left-hand side, we show a standard neural network or feed-forward neural network, where we have some input that we propagate through the neural network layer by layer, alternatively applying linear and nonlinear layers, where there's no parameter sharing between the layers. In contrast, deep equilibrium models, or DEX, apply the same layer iteratively until we've reached a fixed point. This can also be seen as an infinite depth model with parameter sharing. Now, MONDECs specifically, or monotone operator deep equilibrium models, use a specific parameterization that guarantees the convergence and uniqueness of the fixed point. If we view some pseudocode of a MONDEC and see what specific properties does it have for abstract interpretation, we observe a couple of things. First of all, we have to deal with an unbounded loop with a complex termination condition. Both our iteration state and our input are very high dimensional. This is like hundreds or thousands of dimensions. And the iterator itself is highly nonlinear and non-convex, so this is quite a challenging problem. So how can we apply abstract interpretation here? Let me start with a very simple example where we have no control flow. We encode the precondition using asserts, ensuring that our input is between 0 and 2, have a program statement that simply increments the value by 1, and the post-condition where we want to show that the output is smaller than 6. We can use the simple interval domain to over-approximate or abstract the program states each line and show that the post-condition holds. For a slightly more complex problem, we have a bounded loop that we execute 3 times, and now we want to abstract the program state over each of these iterations. We can do this by joining the states at the program loop, so in this case, effectively computing the union over the corresponding intervals, and after a couple of iterations, we indeed observe that the output is guaranteed to be smaller than 6. Now, for a slightly more complex problem, we have an unbounded loop. Here, we do not know a priori how many loop executions we'll do. So we need to approach this slightly differently. But again, we apply the same approach, we iterate, we join in the loop head, and now we notice at some point that the termination condition is satisfied for some but not all of the abstract trajectories. Here we need to abstract the termination condition itself, in this case effectively corresponding to computing the pre-image of the termination condition being satisfied and not satisfied, and then intersecting our abstractions with these pre-images. This yields no change in the loop body and easily allows us to certify again that the output lies between, in this case, 4 and 5, and is thus smaller than 6. However, notice how crucially important the abstraction of the termination condition is here. If you replace the termination condition with a black box function or something that's simply too complex for us to analyze this way, we do get both termination problems and we lose a lot of precision, thus effectively being unable to certify any interesting properties. However, if we focus on a narrower class of unbounded loops, namely fixed-point iterators with uniqueness and convergence guarantees, such as Mondex, we can leverage the mathematical invariant enforced by the termination condition, namely that we reach the true mathematical fixed point of our fixed-point iterator, to focus on abstracting the mathematical fixed-point set of this iterator instead of the whole program. And we'll do that as follows. We have obtained our abstract iteration state as head n, and now apply a single iteration of the abstract transformer G# of a single fixed point iteration. We thus obtain the blue as head n+1, and if we now can show that it's contained within the prior state, this will entail that it contains the true mathematical fixed point set, and I'll now demonstrate why. Let us concretize this abstraction and apply the concrete fixed point iterator to all the points in this concretization. This will give us a set of states that is contained in the blue abstraction by the soundness of our abstraction. And now, by induction, we get that actually all future concrete fixed point iteration states will be included in this blue abstraction. And thus, by the convergence guarantees in the concrete, we obtain that actually it will include the true mathematical fixed point set. Notice this does not necessarily apply to the abstract states, as there we have neither convergence guarantees nor monotonicity properties. And now that we have this general framework for how we can abstract fixed point iterators with uniqueness and convergence guarantees, let us try to instantiate it with an abstract domain. For this, we require the abstract domain to support efficient propagation through our abstract iterator, as we need a couple of hundred iterations for most properties. It needs to support tractable inclusion checks, as each of these iterations includes an inclusion check, and it needs to be sufficiently precise to enable us to certify the properties of interest. Let's consider some domains popular in neural network verification. The Zonotope here, an example is illustrated in the upper right-hand side, is a linear projection of a p-dimensional unit cube into the d-dimensional space, or perhaps more intuitively, a point-symmetric polyhedron that we can write as a product of an error matrix A and some error terms V, which can range from -1 to 1, plus some offset. However, unfortunately, both propagation and inclusion check are quite computationally expensive, making the analysis using the Zonotope domain intractable. A much simpler domain is the box domain, which corresponds to simply axis-aligned hyperrectangles or dimension-wise intervals, which can also be written as a Zonotope with a diagonal error matrix. We illustrate an example that is the smallest box which over-approximates our blue Zonotope in the upper right-hand corner. While it enables very efficient propagation and containment checks, it does not support sufficiently high precision to actually verify any of the properties that we're interested in. We thus propose the so-called CH-Zonotope, which is a Minkowski sum of a box and a Zonotope, and can be nicely written as just that, where we first have a Zonotope component and then a box component. You might have observed that we can write each CH-Zonotope as a simple Zonotope, but we have one crucial distinction. We call a Zonotope a CH-Zonotope with a Zonotope error matrix A that is invertible proper and otherwise improper. This properness will become crucial for our efficient containment check that I'll introduce in a second. Indeed, this properness, if we enforce it, also enables us to maintain a constant representation size in contrast to a standard Zonotope, which then also enables efficient propagation. We illustrate a CH-Zonotope, a proper CH-Zonotope in the upper right-hand corner in green, comparing it to the original Zonotope in blue that it over-approximates, and a box abstraction in orange. Now, as mentioned before, the properness of the CH-Zonotope is crucial. Unfortunately, abstracting a ReLU layer will turn a proper CH-Zonotope into an improper one, and thus we need to reverse this process. For this, we can use error consolidation or order reduction via over-approximation. We are given a green improper Zonotope. We provide an error basis A tilde, and then compute the tightest, soundly over-approximating the proper CH-Zonotope, here illustrated in gray, and for more details, I refer you to the paper. Now we can do an approximate containment check enabled by this error consolidation. Here we want to see if the red improper CH-Zonotope is contained by the green proper one. As a first step, we consolidate the errors of the red improper CH-Zonotope using the error basis of the green proper one, and here it is crucial that the green Zonotope is indeed proper, because otherwise its error matrix would not be invertible. And now we observe that we have obtained two Zonotopes with perfectly aligned faces, and which we can now decompose into their Zonotope and box components and conduct a component-wise containment check, which becomes trivial. Now, putting both of these together, we obtain a state-of-the-art certification method for monotone operated deep equilibrium models. Comparing them with the prior state-of-the-art semi-SDP, which is semi-definite programming based, we observe that we are more precise in all cases, certifying up to twice as many properties, while being also up to 1,000 times faster. However, unfortunately, we also observe that Mondex in fact do not solve or escape the robustness accuracy trade-off. We believe this has two key reasons. The first being the special parameterization required to ensure the convergence properties that we rely on actually induce strong regularization. And the second being the complex analysis that is required to analyze Mondex in the first place limits the scale of the Mondex and thus also their performance. However, our method can also be applied to analyze other numerical fixed-point iterators, such as the householder method. Here we show a comparison to the popular clean iteration for two different input ranges. And in the center we see for a moderate input range, Craft obtains a much more precise over-approximation of the reachable set, here illustrated as a shaded blue region, compared to clean iteration, heeding the shaded red region, and almost recovering the exact ranges. As we increase the size of the input region, we see the clean iteration diverges, while in this case, Craft still obtains a very precise over-approximation of the reachable set. So to summarize, we've introduced an abstraction approach for fixed-point iterators with uniqueness and convergence guarantees in the concrete, and combined it with a novel abstract domain, the CH-Zonotope, equipped with an efficient approximate containment check, which together yields state-of-the-art verification for monotone operated deep equilibrium models and can also be applied to more general fixed-point iterators with uniqueness and convergence guarantees. With this, I want to thank you for your attention, and I'm happy to take any questions.
Any questions? Okay, I'll start us off. Thank you for this interesting talk. So it seems that your ability to sort of divide this thing into these fixed points is rooted in these convergence tests, which is part of the algorithm. I'm wondering, in the course of sort of validating, if you have some kind of a notion of how brittle this convergence test is, if you can simplify it or detect that it might sort of throw off this, this computation.
A good question. So in general, there is a guarantee that if we had an exact abstraction, then we would always have convergence. However, our convergence test requires a contraction effectively of the state, and this is generally not guaranteed to occur. What we've typically observed is that in all cases that we analyzed, so for all properties that we analyzed, we did find fixed point sets, so there this was not a problem. However, when we tried to scale to notably larger networks, then we observed these problems where we actually got a divergence of the abstraction because simply the CH-Zonotope is still not precise enough to prevent this.
Thank you.
It seems like your specifications are all these like fixed zones on the output. Is it possible to like use your method to verify something that depends on the input?
Generally, we can also verify properties that are jointly over the output and the input. this is simply in the space of neural network verification, not so typically done. So we have not looked into this into more detail. But in general, we can verify any linear property over arbitrary inputs and output combinations. Thank you.
Any other questions? All right, let's take the speaker again.
Thank you.